Bismillahirrahmanirrahim. Assalamu alaikum. The topic of this video lecture is complex numbers. Today we will discuss in this video lecture complex numbers and set of complex numbers. This is the title of chapter number 1, first year course. Before to discuss the complex number, the history of a complex number, application of complex number, and different concepts regarding complex number, we need the background knowledge to study the concept of a complex number. So first of all, we will discuss the background knowledge for the concept of complex number. Remember that mathematics is cumulative. Cumulative means for a certain concept to understand, you must need to know the background of the topic. Otherwise, if you didn't know the background, you will just remember the formula or you will just memorize the method and you will just able to solve the question. You will never understand the concept regarding that topic. So that's why before to discuss the complex number, we need to know that why complex number is necessary. What is the reason that we are studying complex numbers, set of complex numbers? Before the set of complex numbers, there are different set of numbers. So what happened that those sets become insufficient and we need another set which is a complex number. So inshallah in this video lecture we will discuss the background knowledge which is necessary for the conceptual study. Then we will discuss this important question regarding the study of the complex number. That's why we need a complex number. And then we will discuss the brief history, definition and different concepts of complex numbers. So before to discuss the complex number, we need some important sets of numbers. So first of all, we will briefly discuss some important sets of numbers. Therefore, invented or discovered before the set of complex numbers. So those important sets are some important sets of numbers. Background study for the complex numbers. The first one is set of natural numbers. We know that every set is denoted by capital letters. So the set of natural numbers is denoted by capital N, and the natural numbers start from 1, 2, 3 and so on. These are the discrete numbers. After 1 you will jump to 2 and then after 2 you will jump to 3 and so on. Natural numbers are also called counting numbers. Remember, counting numbers. This set of natural numbers is written in the tabular form. You already know from the previous classes that there are three methods for writing a set. The first one is descriptive method, the second one is tabular method, so this is the tabular method, and the third one is set builder notation. So this tabular form is also called roster form. This tabular form is also called roster form. Different books give roster form instead of the tabular form. Now this is a set of natural numbers. So which is used for the counting. After this set, we will shortly discuss the set of whole numbers. Set of whole numbers contain non-negative integers. So we didn't know integer. We will discuss set of integer in this here. Now set of whole numbers are denoted by capital letter W, and this contains 0, 1, 2, 3, and so on. So you clearly see that the set of whole numbers is actually a superset of the natural numbers, or in other words, you can say that natural numbers are the subset of whole numbers. So, if we come over to the diagrammatic representation of these two sets, so you clearly see that the set of natural numbers is totally contained in the set of whole numbers. Means the set of whole number is a superset for the set of natural number, or in other words, you can say that the set of natural numbers is a subset of a whole number. You all know the definition of a subset. If we have two sets, subsets. Let's say we have two sets, set A and set B. So set B is said to be a subset of set A if all the elements of set B lies are contained in set A and set A contains other element which is not present in B. So then we can say that B is a proper subset of set A. So this is the notation for the proper subset. B is a proper subset of set A. And if every element of set A is in set B and every element of set B in set A, so then you can say that both sets are equal and every set is a subset of itself. So that subset is called proper subset. So this is the previous knowledge. Now, so this is a whole number. Now coming over to the set of integers. Set of integers are denoted by capital Z, and set of integers contain 0, 1, 2, 3 and so on, and -1, -2, -3 and so on. Mean set of integers contain all the whole numbers, mean all the natural numbers, and then obviously 0 is also there, so all the whole numbers. And then this set also contain -1, -2, -3, and these three dots means that after -3 you will get -4, -5, -6, -7 and so on. So you clearly see from this set of integer that this set of integer is a superset for the set of whole number as well as for the set of the natural number, or in other words you can say that the set of natural number and the set of whole numbers are the subset of set of integers. So diagrammatically you can make like this. This is the integers. So you see that the set of integers contain both whole and natural. Actually natural number is a subset of the whole number, so it no need to say z contain n. If you say natural number set of integers contain whole number, so it is obvious that z will contain n because n is a subset of w. Okay, so this is about the set of integers. Now point number 4, set of rational numbers. Set of rational numbers are denoted by q. Q is taken from quotient because the every rational number is written in the quotient form. This q, which is a notation for the set of rational number, is taken from quotient. Quotient means division. So if you see to every rational number, they must be written in the quotient form, in the division form. Now coming over to the definition of the rational number, there are two types, there are two different definitions of the rational numbers. You see to this one, this is the definition of the set of rational number written in set builder notation. This is the method. This is also the method for writing a set. This set of rational number is written in the set builder builder notation. Now we will first explain this definition of the rational number, then we will briefly explain the second definition of the rational number. Now this set builder notation says that x such that x is equal to p by q, where pq belongs to set of integers. This is a notation for belongs to, this is a notation for set of integers, and this is notation for and q is not equal to 0, means denominator will be never 0. Remember that in mathematics division by 0 is not possible. I will explain it later, that why division by 0 is not possible. But first of all we will discuss the definition of the set builder definition of the rational number. So this x is arbitrary. This x represent maybe any number, this x is arbitrary, this x represent any number, but if that number is written in the form of p by q, for example if I write 1 by 2, so you see that this is the quotient form. The value of p is here 1 by 1 and the value of q is 2, so this is your x. Now this x is take the specific value 1 by 2, so now this p is equal to 1, q is equal to 2. Now this is p by q form. Then you will check that either both p and q belongs to set of integers or not. This is the x, these are the two conditions that you must check for the rational number. If a number is written in p by q form, then you will check that either p and q belongs to set of integers or not, and after that you must check that q is not equal to 0. If q is equal to 0, then that fractional form and then that quotient is undefined. In mathematics division by 0 is not possible. So you clearly see that the value of p is 1, the value of q is 2, and both are integers. Both these numbers 1 and 2 lies in the set of integers. You clearly see that 1 is here in the set of integer, 2 is here in the set of integers, so both are integer. So you see that this condition is satisfied for this specific value of x 1 by 2. Then you will check that q is not equal to 0, so this is the second condition. Now clearly you see that q is equal to 2, the value of q is 2, so that's why q is not equal to 0. So this implies that this 1 by 2 is a rational number according to this definition. This 1 by 2 is a rational number. So this is the way to check the quotient form, that it is a rational or it is not a rational. If I take, let's say 7 by 13, or if let's say if I take minus 7 by 13, so now this is the quotient form, this is the quotient form. The value of p is minus 7, the value of q is 13, so clearly both p and q from the set of integers, and q which is equal to 13 not equal to 0, so this fractional form is also a rational number. Now this is the first definition of the rational number. Now we all know that every quotient form can be converted into a decimal form, or you can say that every fractional form can be converted into a decimal form. For example, in this case, if you divide 1 by 2, you will get 0.5. So if the decimal form of a number is given, then how you will check, then what is the procedure, then what is the definition that this 0.5 is a rational number or this 0.5 is not a rational number. Actually this 0.5 is equal to 1 by 2, and we know from this definition that 1 by 2 is a rational number. But if someone asks from you that what about 0.5, it is a rational number, then how you can justify your answer that this is a rational number? So for decimal form of a number we use another definition, that is, if a number is given, then how you will check that this 0.5 is a rational number. Actually this 0.5 is equal to 1 by 2, and we know from this definition that 1 by 2 is a rational number. But if someone asks from you that what about 0.5, it is a rational number, then how you can justify your answer that this is a rational number? So for decimal form of a number we use another definition, that is, if a number if a number of digits after the decimal point are terminated or stop. For example, you see that in this case, after the decimal point, you clearly see that there is a single digit 5, and after 5 there is nothing. After 5 this number is stopped. So if in a decimal form, after a decimal, if the number of digits are finite, then you can say that this decimal form is also a rational number. Or for example, if I take 1 by 3, 1 by 3 according to this definition is a rational number. 1 is the value of p, 3 is the value of q is not equal to 0, and 1 and 3 are set of integers from the set of integers. So this is a rational number. But now if you divide 1 by 3, so you will get 0.333 and so on. So we can write this like 0.3 bar. This bar represents that this 3 repeats infinitely. Now after the decimal point, you see that this digit is not finite. This is infinite. This is not finite, but it repeats itself. There is a pattern. After 3 you will get 3, 3, 3, 3, 3, 3 and so on. So if there is a certain pattern after the decimal point, so then that decimal form of a number is also a rational number. Now if I take 1.73457 and so on, now in this case after the decimal there is no repetition, and after the decimal the number of digits are not finite. The number of the digits are infinite. So that's why this number is not a rational number. So this is the brief discussion about the rational number, that how you can check a number is rational or not a rational number. So this is the brief discussion. Another question arises here that we write the above three set of natural numbers, set of whole numbers, set of integers in tabular form, and in point number 4 we are writing the set of rational number in set builder notation. So why we are not writing the set of rational number in the tabular form? So the reason is that in the prior 3 cases, for the natural number, for the whole number, for the integers, if I write some natural number, if I write some integer, if I write some whole number, so after that number you exactly know the previous or the coming number. If I write, let's say 10 is my natural number, so I exactly know that coming natural number must be 11. If I write -4, an integer, so I know that after -4 the next integer is -3. So in the prior 3 cases we know exactly that after every number which number will come. For example, after 10 you will get 11, you must write 11. After 11 you must write 12. So you know that after 10 you will come on 11 and 12 and so on. So you know the sequence in the prior 3 cases. But for the set of rational number we didn't know. If I write 1 by 2, this is my rational number, so I didn't know exactly that what will be my next or what will be my previous rational number to 1 by 2. For example, 1 by 2, you clearly see that 1 by 2 is equal to 0.5. This is a rational number. So if I write 0.5, this is my rational number. So after this 0.5, I didn't know that what will be the next rational number. What will be the next rational number? If I write after 0.5, let's say 0.51, is my rational number. So it is not correct that after this rational number you will switch to this rational number. No, before in between these two rational number we have infinite number of rational number. This is a result that every two rational numbers, in between every two rational numbers there are infinite rational numbers. So you cannot write the set of rational numbers in the tabular form. That's why this is the best method for writing the set of for writing such type of sets in which you didn't know that what will be my next number. So in case of the rational number we didn't know that what will be our next number. So this is the set builder notation. You clearly see that x is arbitrary. X may be anything, but if it satisfies these three conditions, it must be in p by q form. Both p and q belongs to set of integers, and q must not equal to 0. So this is enough for the set of rational number. These all points are already discussed in the previous lectures. Sorry, in previous classes, but we repeat it here for the sake of the concept of the uh, complex numbers. Now moving towards the set of irrational number. Now you clearly see that one another point here. You clearly see that every integer is a rational number. For example, if I consider an integer, let's say I am considering an integer 4. This is my integer. Now this 4 is can be written in p by q form. 4 can be written as 4 by 1. So this is equal to p and this is equal to q, and this value of p is for integer, q equal to 1. This is integer, so both are integers and q is not equal to 0. So this integer is also a rational number. So from here we can say that every natural number is an integer. Every integer is a rational number, and every whole number is also a rational number. So it means that all these three set of natural numbers, set of whole numbers, and set of integers are rational numbers because they can be written in the form of p by q. So 0 is also, remember, 0 is also a rational number because 0 can be written as 0 is equal to 0 by 1 or 0 by 2 or 0 by 3 or 0 by 3. So this is the value of p, this is the value of q. So p is 0, q is 1. You will see towards the q that q must not be equal to 0. So this is also a rational number. So in short, every integer is a rational number. So when you say every integer is a rational number, so it automatically means that every whole number and every natural number is a rational number because whole numbers and natural numbers are the subset of integer. So here clearly we can make a diagram like this. So this is the q. So now you see that q contain all the three sets. So this is the set of rational number. Now a number which is not a rational number is called irrational number. A number which is not a rational number. A number which is not a rational number is called irrational number. So for example, if I take square root of 2 divided by 3, so this is p by q form. But now the value of p here is square root 2, and we know that square root 2 is not a rational number. Square root 2 is not a rational number. If you find out the square root of 2, you in the decimal form, after the decimal the number of the digits are neither repeated nor terminated. So that's why this square root 2 is not a rational number. This is also a rational number, but we are actually discussing that under the root 2 divided by 3 equal to p by q, and we are discussing that this is not a rational number because this under the root 2 is not an integer. This is not an integer. So that's why this p by q form is not rational. So if a number is not rational, then those numbers are called irrational numbers. Those numbers are called irrational numbers, and irrational numbers are denoted by q bar. Now, at last we are moving towards the set of real numbers. Set of real numbers are denoted by capital Q, and this is equal to the union of rational and irrational numbers. Now, when you combine rational and irrational numbers, now in this diagram, you see that irrational numbers doesn't contain any of the prior four sets. So in a diagram, I will write this portion. I will choose this portion for the irrational number. Now, set of real numbers are actually defined as rational union irrational. So when you combine all these numbers along with irrational, so you will get set of real numbers. You will get set of real numbers. So set of real numbers contain all the rational and all the irrational. So when you say that R contain all the rational, so it's obviously it's obvious that R contain Z, R contain W, R contain N. In other words, you can say that every natural number, every whole number, every integer, every rational, every irrational is a real number. So up to now, the largest set or the biggest set in all these sets is set of rational numbers. Because set of rational number contain all the other sets. So this is the brief discussion about the some important sets which gives the foundation for the set of complex numbers. Now we will briefly discuss the geometrical meaning of the real numbers, and then we will switch to the topic, which is a complex number. And obviously we will explain now this question. We will discuss the background of the topic, mean different sets we discussed. Now we will discuss this question. That's why we need a complex numbers. So in brief, now coming towards the geometrical representation of a real number. Geometrical representation of real number. So I am just writing the R, capital R. This is notation for the real number. There is a 1-1 correspondence. You all know this point. This line is made from infinitely many points, and the set of real numbers are also infinite because it contains rational, irrational, and so on. So they are infinite in numbers, and this line is also made from infinitely many points. So in 1-1 correspondence, we assign a real number to a point on a line, and each point is assigned or each point is labeled with a real number because both are infinite. So for every point we have a real number in the set of real numbers, and for every real number we have a point on the line. This is called 1-1 correspondence. So there is 1-1 correspondence between the real numbers and the set of points which make the line. One correspondence means for every point on the number line we have a real number from the set of real numbers, and for every real number we have a point. In a diagram you can see, let's say this is a number line, and let's say this is a set of real numbers. So for every point on a line you must have some real number here, and for every real number you must have some point on the number line. So this is called one correspondence. Now let label this point with 0. uh, Basically 0 is an important number. It is used for the reference, because when you want to uh, do some measurement you must need a reference point. So this 0 is used as a reference point for the set of real numbers. So now let's say this point is assigned with 0. Now I am assigning this point let's say with 2. So what 2 geometrically mean? 2 is actually geometrically 2 units away from this reference point. It means that 2 is this 2 is actually this point. So this point is 2 units away from the reference point. So this is the geometric meaning of 2. If I take -2, so the geometric meaning of -2 is this point to which we assign -2 is actually 2 units away. This distance is also a 2 unit distance, and this distance is also 2 unit distance. But the point which lies on the right of the reference point is conventionally considered positive, and the point which lies on the left side is conventionally negative. So this minus sign is just shows the direction. This -2 is assigned to this point. So this point is actually 2 units away from the reference point, and this point is also 2 units away from the reference point. But this is +2 and this is -2. So this minus just shows the direction, that this point lies on the left of the reference point, and this plus shows that this point lies on the right of the reference point. So this is in brief the geometrical representation of a real number. In mathematics, three things are very important for every topic. In mathematics, you must know about the symbols, you must know about the notation, and if possible, geometrical meaning. So I explained the geometrical meaning of real numbers, geometrical meaning of a certain concept, and we discussed the notations and symbols in these important sets. Now coming over the question that why we need to study the set of complex numbers. Remember that every real number square is always positive. If you take the square of every real number, the square of every real number is positive. That is, let's say x is a real number, x belongs to real numbers, so x square must be greater than 0. This is actually also a definition of the real numbers, that if you can choose any real number, x square must be greater than 0. Now another question, is it possible, is it possible that square of a number is negative. If this is possible, up to now we know that the largest set is a set of real numbers. Every number which comes to our mind is a real number up to now. But now the question is that if there is a possibility that if you can take a square of a certain number and it gives a negative result, is it possible? So at that point it comes into the mind of a different mathematician that there must be some other numbers which not belongs to set of real numbers. For example, if I write a simple equation, x square plus 1 equal to 0. Now this is a quadratic equation, and you know about the quadratic equation. So this is a quadratic equation. Now if you see, this x square is equal to minus 1. So now x may be some number and the square of that number is equal to minus 1. So at that point the mathematician thinks that if we take the square of a real number, you will get a positive result. Now if we take the square of a number, in this situation you see that this is equal to minus 1, mean negative, less than 0. So they think at that point that there are some numbers which are not included in the set of real numbers, and then they say that set of real number is not the biggest set, that does not contain all the numbers. There are some numbers which are not in the set of real numbers. So this is the point. When you are solving this quadratic equation, you must get some numbers which is not included in the set of real numbers. For example, if I want to solve this equation, so this will be equal to x square, taking square root on both sides. So this will be equal to plus minus square root of minus 1. Now this square root of minus 1 is not a real number. This number doesn't belong to set of a real number. Now this is a number, but this is not included in the set of real numbers. So this is the reason that mathematicians think that set of real numbers doesn't cover all the numbers. There is some numbers which is not included in the set of real numbers. So this is the whole story about the complex number. This is named by this under the root minus 1 was introduced by Euler, and the name iota was given to this number by Euler. After that, different mathematicians, Gauss and different other mathematicians study these complex numbers. We will discuss a complex number, but this number is named iota, and this name is given by Euler. So this is a number which is not included in the set of real numbers. So at that point we get that real numbers are not sufficient. There is some numbers which are not included in the set of real numbers. So this is the reason that we are studying the set of complex numbers, because set of real number is not covering all the numbers. There are different numbers which are not included in real numbers. So that's why the necessity for the study of complex number came. So inshallah, in next video we will discuss the real life application and the concept of the complex numbers. So but this is the background study, this is the whole story about that why we need to study complex numbers. So inshallah, in the next video we will discuss certain concept about the complex number, the definition of the complex number, and real life application of the complex number.
Thank you.